Welcome everyone. Again, welcome to PyData Global. This is our final day. Please remember that you can chat and share your thoughts in the chat box. And without no further ado, help me welcome our speaker and give us a warm virtual welcome. Take it over, Jayita.
All right, thank you. Thank you so much for having me. So I hope my screen is visible and let's get started. So today we'll be discussing about SLMs or small language models, which are the younger and mightier brothers of LLMs. I call it how big are SLMs because not because of the size, but because of the amount of work and with optimal resources that they can do. The idea of this session is that the in artificial intelligence landscape we have been dominated by the paradigm that larger is better, and we have seen that the massive generalistic LLMs like GPT-5 and any LLM model that I'm sure all of you might be using. These models are really great. They exhibit a really remarkable emergent abilities. Their operational paradigms represent significant challenges. The immense size, although there is a downside to it that the immense size leads to some prohibiting computational demands during training as well as inference. And even if you want to fine tune it, or if you want to go for some privacy concerns that is associated to your own domain specific data, so there is a nature of these models that they perform well when there is a generalistic nature of these models, but when you want to do it in a domain specific way into healthcare, law, or anything else, they are not that efficient. So in response to combat these challenges of LLMs, SLMs are the new shift that is happening. And over past, I think, 1.5 years, there have been massive evolvement of SLMs, and we'll be seeing that not only in text but into multimodals, into more kinds of reasoning models, say VLMs or VLAs, and many different kinds of paradigms of SLMs have been coming up, and they are really efficient in terms of cost, in terms of the specialization they bring in. And the core disadvantage of LLMs, that is these bigger size and that harder deployments that you have to make. And SLMs can be deployed onto your edge devices, any IoT, or even your mobile phones. So these are the greater things that SLMs can do. They provide you with more privacy, where you can handle all the complexity, and you can do fine tuning, and you can have a better domain specific model. So I'm sure you must have been hearing all the buzz around SLMs, and these are the common ones there. I think Small LM 3 has now come out. Gemma 3 by Google has come out. Small LM is by Hugging Face. Gwen by Alibaba. Mistral, and then Phi 4 by Microsoft. Llama 3.2, which is this great 1 billion and 3 billion parameter models that I tried it out with Olama into my local system, and I just have a 8 GB RAM. And even with lesser, I think even with 4 or 5 GB, 4 or 6 GB RAM also, it really works well. So that's the thing that we are trying to solve, that for specialized tasks, these small language models can work in a very restricted way into even with a smaller compute power, they can provide you better results into domain specific world. So let's understand what do we call a small language model. So in terms of size, if you have to say, generally between 1 million to 10 billion parameter models is what we call as SLMs. Also, although this is a bit debatable, I think NVIDIA Nemotron has 12 billion model as well, and even 30 billion models also are at times considered as small models. But the idea here is that, yeah, generally around 10 billion model, we would consider that as a small language model that is very manageable in terms of scale. With within limited resources, they are capable of performing specialized tasks. And the goal is not to replicate the general intelligence that LLMs bring in, but to achieve the state of the art performance with a controlled and well defined scope within your domain specific tasks that you want to achieve. So yeah, why do we need SLMs? I think I've already been bragging about all of these, that they are cost effective in terms of whether you have a well, in terms of a big model, when you have to bear the cloud API cost if it is a closed source model, or you have to bear the infra cost if it is the open source models. So in terms of that, if you deploy an SLMs, it is also easier to deploy because it's smaller in size and it's also cost effective. It works very good. It gives you faster inference and can work well into edge devices, because we cannot run bigger models onto our edge devices. Offers very low latency, of course depending on other factors as well. Takes in less memory, works with very less computational challenges. So this is a again a AI generated image that I used the Notebook LM infographic. I used the Notebook LM infographics to generate it, and this was a very great thing that it compared how SLMs actually work in terms of, say, the massive computational. If you are following up the news, you would see the carbon footprint is a big challenge in terms of maintaining these LLMs, and there are bigger and more data centers need to be coming up in terms of LLMs to keep these LLMs hosted. In comparison, SLMs do not require that much of power. They can work even in your local systems as well. And again, there are privacy risks. If you have seen earlier, the ChatGPT had leaked user data that it obviously uses, like whatever is free, it is regarded that your whatever you input, it is being used to live train the model as well. Whereas in an SLM, it is completely in your power, it is in your system that you're running, so you do not need to have this thought of that your data is going out of your network. So these are kind of the good things that SLMs have. They can be deployed onto edge devices. There are like very good models now. I think earlier the challenge was that SLMs were not performing at par with LLMs or onto certain tasks. But now with the models like Gwen 3 and more, they are able to perform really well in terms of the accuracy that is achieved on simpler tasks, say any classification or summarization task. When compared to an LLM, they are giving at par answers. So accuracy is something also that is maintained. And of course, you can do knowledge distillation, fine tuning on top of these models. So say suppose you already have a base model and you just want to train your own domain specific task on top of it. So you just go for fine tuning using LoRa, Preft, or any other technique that you wish to apply. So yeah, as I was discussing that earlier, the challenge was that these there were only text models that in the space of small language models, there were only certain text-based models that were there. But now it's becoming more generalistic. There are multimodal SLMs as well. There are reasoning models, and they can, as I was mentioning, that onto certain tasks they are performing at par with LLMs. So this is one paper. I will share the link to the slides, no need to worry, and you can maybe go on and dig deeper onto this paper. So let's discuss about certain training techniques that are adapted onto SLMs. So training an SLMs from ground up is a very strategic decision that an organization does seek very deep specialization on complete control over the model's architecture, data, and behavior. While often more resource intensive than adapting pre-existing models, this approach follows for creation of a highly optimized asset tailored to specific domain. It serves as a foundation method upon which more advanced techniques such as distillation and specialized fine tuning can be built. So, if we discuss about the pre-training strategies, which is a foundation step into constructing SLMs, where mixed precision training has emerged as a critical method for enhancing efficiency. This approach employs low precision representations during forward and backward propagation while retaining high precision weights during revisions. For instance, say automatic mixed precision or AMP. This maintains a master copy of weights in 32-bit floating point FP32 precision while performing computations in 16-bit floating point FP16 precision. Despite its utility, the accuracy issues due to FP16's limited numerical range that were noted in certain papers that came out. So this was addressed by bfloat 16, which offers an enhanced dynamic range and adapt additional exponent bits, leading to superior training performance and numerical stability compared to FP16. And of course, all of us know that NVIDIA's GPU architecture, if you consider Hopper, it further enhances these capabilities by supporting 8-bit FP8 precision, facilitating greater computation efficiency without promising accuracy, without compromising on accuracy. Its specialized tensor cores in these GPUs enable quicker training for both SLMs and LLMs. So, to complement mixed precision methods, optimization techniques such as ADAM-W, and memory efficient variants like ADA factor are widely employed. Gradient clipping is a method that prevents from exploding gradients, while effective initialization strategies ensure a stable starting point for training. These combined approaches enhance efficiency, they stabilize the training process, and improve the robustness of resultant models. Distributed training has become an indispensable for pre-training SLMs. They leverage multiple machine nodes to manage large data sets and models efficiently. Techniques such as zero redundancy optimizer and PyDot's fully sharded data parallel dispute training states across devices. Zero, for example, partitions optimizer states, gradients, and model parameters across nodes, while FSDP implements similar concepts to facilitate larger batch sizes and enhance stability. There's also resource efficient fine tuning, which minimizes computational overhead by updating only a subset of model parameters and integrating lightweight models, leaving most pre trained models on weights unaltered. These approaches like LoRa, which employs low rank decomposition, and prompt tuning, which introduces learnable parameters, exemplify PEFT methods. Llama adapter extends this by adding prompts to Llama's attention blocks, enabling task-specific alterations with minimal resources. So yeah, I can go on, and there are like multiple things that can be done here. There is mixture of experts is an architecture that can be followed that enables multitasking and mitigating the catastrophic forgetting. Data augmentation is also a potent technique to enhance the diversity, complexity, and quality of training data, as we have seen in earlier days of traditional machine learning, that by augmenting data sets, models generalize better and perform robustly in subsequent tasks. For example, AugGPT generates rephrase training samples using GPT, while Evolve Instruct employs multi-step revisions to create diverse open domain instructions. Reflection tuning refines both instructions and responses using GPT-4 to enhance instruction response consistency. So there are certain compression techniques also that have been evolving over the years. Pruning strategies that strive to minimize the number of parameters in a model, boosting computational efficiency and decreasing memory use while preserving the acceptable levels of performance. There are two basic ways to pruning, and are unstructured and organized pruning. If you go for fine grained pruning, this strategy eliminates individual weights of lower relevance, enabling fine-grained control over model size. For instance, sparse GPT reformulates the pruning process as a sparse regression problem, enabling efficient pruning for big models like OPT 175 billion and Broom 126 billion. Wanda analyzes both weights and activations, minimizing the requirement for weight updates during pruning. The N is to M pruning approach prunes exactly N weights out of every M, balancing flexibility and efficiency, and is exploited by NVIDIA's TensorRT to speed inference on GPUs. If you wish to go for group-based pruning, unlike fine-grained pruning, group-based pruning removes entire groupings of parameters such as neurons or channels, which allows implementation on standard hardware. Methods like contextual sparsity dynamically prune neurons based on input, maximizing computational efficiency. Additionally, approaches like as FastGen focus on eliminating duplications in transformer layers, enabling more effective use of GPU memory and faster processing performance. There are these recent works which have examined input dependent pruning algorithms such as dynamic sparsity, which adjust pruning tactics to individual inputs and increase performance. Structured pruning techniques remain vital for enabling hardware accelerated compression without compromising on the model efficacy. There is precision optimized quantization. So quantization is a frequently utilized approach for compressing LLMs with huge parameter control. This strategy decreases the model size and computing need by encoding weights and activities with low precision, such as 8-bit integers. Weight precision approaches like GPTQ accomplishes layer-wise weight-only quantization, reducing reconstruction error, while Bayesian matrices, using Bayesian inverse matrices. AWQ and zero quant expand this method by considering activations alongside weight, optimizing the trade-off between precision and computational efficiency. So there is other efficient active quantization techniques like smooth quant and spin quant that you can maybe go through. For sake of time, I'll move on to like knowledge transfer techniques that you can apply. So these techniques move knowledge from a bigger pre-trained instructor model to a smaller, more efficient student model. Uh, this approach minimizes model size value by retaining performance and making it efficient technique by developing SLMs. So there are traditional transfer learning knowledge transfer methods that are there, that a teacher-student model consists of. Baby Llama was one of them, where the teacher model, the teacher as the employs Llama as the teacher to generate a 58 million parameter student model, providing that distillation can outperform pre-training in same data sets. There is enhanced knowledge transfer as well, where you can so the recent improvements include sequence level distillation, which employs generalized diverses to increase the response quality, and task aware distillation, which selectively transmits task process knowledge. Multi-teacher distillation techniques combine these outputs from numerous teacher models to boost the performance of student model. There is also supervised knowledge transfer, which incorporates additional monitoring during distillation, has demonstrated to help learning process. So I'm not sure if I'm going a bit fast. If there's any question, maybe I can take it now or maybe at the end. Okay, if there are no questions, then let's proceed to the next one. So yeah, I think this is an overall architecture optimizations that SLMs take up. And these recent models like llama 3, 5, 4, and they use even gemma 3 as well. They use this concept of grouped query attention, which reduces the memory footprint of the kv cache during inference, making them more efficient on devices with limited memory. There is this concept of sliding window attention as well, where so in some models like gemma 3, which uses a hybrid attention mechanism that combines global attention with more efficient localized sliding at window attention to achieve faster inference for long sequences without significant performance loss. And there is so we already discussed how data augmentation and high data quality curation is required. So this becomes a very key factor in model performance. And this really helps into how stronger reasoning capabilities with fewer parameters can be done. Quantization, as we already discussed, that it's a very common post-training techniques to shrink the model size and speed up the inference and enable on-device deployment. Parameter sharing is one other thing that can be done for models like the bird family. They utilize the parameter sharing technique across layers to significantly reduce the total number of parameters that are there. And yes, lastly, it's very important that you have a proper evaluation setup, because you will obviously need to measure the effectiveness of the SLM that across application context that you want to do it there. So this is a breakdown of various settings like and limitations, dataset, and metrics that are utilized while assessing SLMs. So maybe if I go by dataset, so that is the data set that you select and curate is very crucial, that will enable the model to generalize effectively across varied concepts. The typically used data sets for pre-training and evaluating SLMs are in here. These data sets are particularly constructed to satisfy distinct limitations, enabling robust evaluation across multiple use cases. And there is efficient inference. So, in applications where latency and throughput are crucial, models need to create outputs with very little delay while retaining high processing rates. This requirement is particularly critical for real time applications such as question answering, text classification, and natural language understanding. There are some very good data sets like Slooper Glue, Squad, Trivia QA, COQA, and natural questions, which are extensively used for measuring performance in these tasks. Preserving is another very good criteria when building SLMs. With increased concerns about data privacy, privacy preserving datasets play a critical role in facilitating the development of SLMs that can handle sensitive data, sensitive information securely. Privacy Glue is a dataset that applies differential privacy approaches to common tasks such as sentiment analysis, gives a standard for privacy conscious models. Similarly, anonymized datasets like Mimic and N2C24 offer de identified clinical notes for medical applications. Federated datasets like Leaf5 further enhance privacy by allowing data to remain spread across devices, providing privacy by design using federated learning methods. TinyML and on-device models. There are models implemented in resource constrained situations, but that must run effectively without losing accuracy. So frameworks such as TinyBird and OpenOrca provide specific datasets and tools for training and evaluation in such circumstances. TinyBird is a distilled version of BERT, is optimized for both speed and size, making it appropriate for applications with minimal latency. And yeah, there are metrics that you would obviously need. So latency is particularly one of them, and then memory is another, then privacy and energy optimization are the other parameters that you would want to check out. So this is one of the app that Google released. It's called Edge Gallery. You can find it in App Play Store as well as on GitHub. So this is a very great application to show how to run open source models. So the very first thing that you go download when you download this app is that you can go ahead, download a model from Hugging Face and upload it. Even small quantized models can give you very good answers, and you can do multi-turn chat. You can even upload images and scenes, or even audio, and then ask the model questions out of it. There are code generation models as well. So this is a very cool app that I tried out few months back, and I suggest you to look it up. And it's very great that we can actually run these big small models onto our edge devices, into our phones. So yeah, I would recommend checking this out. And there's this concept of hybrid LLMs that there was a video that I came across by Google again. So they talk about how you can or based on the whatever application you're building, you can decide for which tasks you need to use an SLMs, and for which tasks you can use the LLM. So this robust decision making can actually bring down your cost and give you more efficiency on tasks that the SLM can work better, and tasks that the LLM can work better. So hybrid LLMs I think going forward the next that you build your agentic applications onto. This is what can be a very good use of it. And so Hugging Face is again a very great ecosystem they have built, and they have these small models where they have this family of efficient and lightweight AI models that they have. And their vision is to just give the power of these text, vision, and anything that you can run on device with good performance. So they have this vision language action models, as well as the so as I was saying, that not just text but vision language actions, that models that are used in robotics. So based on the understanding of the scene and everything around, the robot tries to learn and take actions on top of it. And there is again VLMs, vision language models that are there. So this is a representation of how the VLM have been evolving from polygemma to now they have, I think, small VLM, which is very smaller in size, and it is at part to so Gwen recently came out with a vision language model as well. So a lot is happening on these smaller models. If you see, a lot of these models are getting coming up, and a lot of advancements on top of this that is happening. So I think, yeah, I went a bit fast, and this topic is really a big one to be covered in such a short time. But yeah, I think these are some of the resources that I was referring. So maybe you can go through that. If you scan this QR, you will get the link to this, and I can paste it on the chat as well. Yeah, on that note, yeah, thank you so much for having me. And if there's shortage of time and you're not able to reach out to me, then feel free to reach out to me over any of my socials, and they're on LinkedIn, Twitter. Yeah.
Thank you so much, Jayita. We do have one question.
Mm-hmm.
Um, Someone said, if you have done all the work to train your model and never and a newer version of the SLM comes out, how do you transfer that to the newer version, or do you need to start again?
So usually what we do is that we try to keep a live training going on. So when we deploy these models, there is newer data coming in, and then we try to, in a week or a two's time, we try to do a retraining again with this newer data. That has been this approach for now. But yeah, surely if the we cannot keep going on with the same architecture always. So there is evolvement onto architecture as well, and there will be like these things that we need to again later on update the model architecture and do a retraining as well. And everything in AI is an experimentation. We cannot say that down the lane, 1 year or 2 years after that, my model will be that great. So yeah, continuous learning and evolvement is something that we have to do.
Thank you. Two more questions. Someone is asking, will it be possible to get a copy of the slides?
Yeah, surely. Let me share that.
Okay, you can share it via the Discord. Um,
Okay, yeah, I'll do that.
Also, someone is asking, how do one run Hugging Face model on Google Edge Gallery, and how can I know that a specific model can run on my phone or not?
All right, I think once you download so Hugging Face models is very easy. Like you go to their you go to the Hugging Face websites and you just download the model weights from there, and then you load this model onto the Edge Gallery app that you have in your phone, and you'll get the options. Like Edge Gallery
Mhm.
will ask you to add the model, and you'll get that option there. And even small models, like I think I tried out 4 billion digital model I tried out, and my phone only has 6 GB of RAM, so with very less compute you can actually have these smaller models run on your devices. So yeah, just try it out.
Okay, well, thank you so much. I know we had one more question, but we are at time and we're gonna begin to wrap up. So I do want to thank
All
you all
right.
for joining us today. If you'd like to continue the discussions, you can head over to the Discord. There's also the lounge area. So if you all wanted to go to the lounge area, if you back out of here, you end up at the reception area, but there's also a lounge where you can go into small groups. A recording of this session will be available shortly after for rewatching. And if you have any other questions, please feel free to go ahead in the small groups. Thank you again, attendees, for attending and have a wonderful day.
Thank you.
Mhm.